All right, this is video 11 for the real analysis series, or baby real analysis series, and we're just going to cover more on sequences. And for this video, I'll discuss the limit laws. We're going to prove the first three. I'll do another video proving the fourth one and the squeeze theorem in another video. But yeah, so these are the limit laws that we're familiar with from like calculus class. So if we assume that we have a sequence AN converges to A, and then a sequence BN converges to B, and we're given a real number C, the first one, the sequence that just only consists of the value C converges to C, so that's a constant sequence. The second one, the sequence where it's C times AN, that converges to C times A. The third one, so if you add or subtract two sequences, then the limits you're going to add and subtract the limits. So AN plus BN converges to A plus B. AN minus BN converges to A minus B. And so for multiplication, if you multiply the two together, you get the product of the limits. So AN times BN is equal to, or converges to AB. And then same thing for division. If you divide the sequences, you get the quotient of the limits. Now that's provided that the denominator B is not 0 and that the sequence Bn is not 0 for all of the indices n. All right, so this isn't anything new here. I just figured I'll go ahead and write these out. And then also the next thing is the squeeze theorem, which we've seen in a calculus class. The squeeze theorem says if I have three sequences and such that for AN is less than or equal to XN, which is less than or equal to BN for all indices n. So we have our sequence XN is sort of sandwiched in between two sequences AN and BN. And we know that AN converges to some value L, and then BN converges to some value L. Then it follows that XN has to converge to this value L. And so just a picture, so we have our indices on the x-axis and what the actual values are for the sequences. It's on the y-axis. And then we're going to say it converges some value L. And eventually, let's see. Eventually, the terms of the sequence get within this sort of our confidence, calling it confidence interval around our limit L. So L minus epsilon, L plus epsilon, and that region is where the terms, this is what I like to call as my confidence region or confidence interval. And again, eventually the terms get so close to get within epsilon distance of the limit L that they are within this confidence region. And there comes a point, so initially at the beginning, our sequences don't have to follow that AN less than X and less than equal to BN. It's just once I get to some point, index n, that it has to be like that. So for instance, in the beginning, let's say A1 is less than B1 and less than X1. And then it sort of switches a bit and you get X2 less than, or B2 is less than X2 less than A2. So it sort of does this weird oscillation, but it comes to a point where after AN, we have it so it's like this. And then BN comes like this. And so all of the BNs, these are all less than the ANs. So these are the BNs less than the ANs. And these ANs are the values that are bigger than the BNs. And notice the gold dots, that's our sequence X, and that's sandwiched in between. Okay, so I just connected it to show visually sort of that's where we hit this point where the index ends, such that for all indices beyond this, we have our values of the sequences such that we have AN less than or equal to XN, which is less than or equal to BN. And if we know AN converges to L, BN converges to L, then XN has to converge to L. So at this point, and we have after that, all of our terms of the sequences lie in this confidence region. And epsilon's arbitrary, so a confidence region could be as small as we want. So we could be zooming in a lot here. Okay, so that is the squeeze theorem. Some other important propositions is a sequence can have at most one limit. And if we have a convergent sequence, then that sequence is bounded. All right, so those are two important propositions. And that's all of the theorems and propositions I'll talk about in this video. Now we're going to go into some proofs. So for the limit laws, we'll try to prove those, at least some of those. And whatever I don't cover in this video, I'm going to cover or continue off in the next video. So the first one says we have the constant sequence C converges to C. So we got to prove that. And this proof is pretty simple, is note that the sequence C is basically the constant sequence. So all of the terms are C. So you have C, comma, C, comma, C. So our A1 is C, A2C, A3C, and then all of them are the same value C. So since they're all the same value C, then given epsilon greater than 0, we can let capital N be 1. So we're letting capital N be the index of the first term. Then for all the terms beyond that, so for all the indices N bigger than capital N, we have that C minus C, which is equal to 0, which is less than epsilon. Now we can pick any index capital N that we want, since all of the terms are the same value C. So just choosing the first index value, N being 1, and then all the N's, or these are all the terms that have indices little n bigger than 1. But they're all the same value C. So the difference between C and the limit C is 0. So it's going to be true for any epsilon. The second one in the limit laws, if we're trying to prove that C times AN converges to C times A, knowing that AN converges to A. So this one I did is wrote out the strategy here. So the strategy is we need to find some capital N such that for all little n bigger than capital N, we have C times A and the absolute value of C times A and minus C times A to be less than epsilon. That's what our goal is. We can use the knowledge that AN converges to A. And what that means is, so we know AN converges to A, so there's another capital N, so there's, some capital N for that case, in which all little n's bigger than that, we have AN minus A to be less than epsilon. So this is true for any epsilon. Now notice we can manipulate our absolute value of C times AN minus CA to be the absolute value of C times the absolute value of AN minus A. And we need the whole thing in our proof. This needs to be less than epsilon at the end. And so how do we do that? Well, this whole thing's going to be less than epsilon if and only if the absolute value of a n minus a is less than epsilon divided by the absolute value of c. So I divide by c. So we're going to use our knowledge that a n minus a is less than any epsilon. So it's certainly true that's going to happen for epsilon star being equal to epsilon divided by the absolute value of c. So we know it works for any epsilon. So let's use epsilon star being equivalent to epsilon over the absolute value of c. Okay, so that way we'll have absolute value of c times am minus a. That's going to be less than absolute value of c times, and we have this is less than epsilon star. And then epsilon star is epsilon over the absolute value of c. So it's going to be absolute value of c times epsilon over the absolute value of c. And the absolute values divide each other out, and which is going to give us epsilon. So we used our knowledge of the convergence of an going to a to find sort of like a bound in which we need in order to get it the whole quantity, the absolute value of c times the absolute value of a n minus a to be less than epsilon. All right, so that's the strategy. Now the actual proof. So given any epsilon greater than 0, assume the sequence a n converges to a, and we're given any real number c. Note that c could be 0 or not 0. If c is 0, it follows that the absolute value of c times an minus c times a is equal to 0 times an minus 0 times a, which is the absolute value of 0, which is equal to 0. And that's less than epsilon. That's true for the entire sequence an. So therefore, it doesn't matter what n we pick. So let's say we pick capital N to be 1 for the index. Then for all indices little n bigger than capital N, we have c times a n minus c times a equal to 0, which is less than epsilon. All right, so the first case, when c is 0, right, we just, the difference, the absolute value of the difference of c times a n and ca is 0, which is less than epsilon. So in that case, it doesn't matter what capital N we pick because it's true for every value n. All right, now the complicated case is suppose c is not 0. So because an converges to a, then we know there's, for all epsilon star greater than 0, there exists a capital N such that for all little n bigger than capital N, we have the absolute value of an minus a to be less than epsilon star. Since this is the case, let's find capital N so that we have the absolute value of an minus a to be less than epsilon star being equal to epsilon over the absolute value of c. All right, so again, we can do this because c is not 0 whenever little n is bigger than capital N. So using this specific choice for capital N, we have that for all little n bigger than capital N, the following. So we have the different absolute value of the difference, c times an minus ca, eventually is going to be this equal to this. And then we know this an minus a, that whole thing is less than our epsilon star based on our choice for n. And epsilon star is epsilon over the absolute value of c. So that, therefore, this whole thing, absolute value of c times absolute value of an minus a is less than absolute value of c times e over the absolute value of c. So then the c's will divide out, so you just get epsilon. All right, so c being 0, I had to do as a separate case because obviously you can't divide by 0. But that's the easy case because then the whole thing is 0. So it doesn't matter what index you pick, it's always going to be 0, which is less than epsilon. And then when the case of C not being 0, we use the fact of that AN converges to A. And by definition, that means for any epsilon star, we have there exists index capital N such that for all little n bigger than capital N, we have that absolute value of AN minus A be less than epsilon star. Since that holds for any epsilon star, we just let epsilon star be equal to epsilon over the absolute value of C for the value of epsilon that were given in the very beginning of the proof. So that way, we get the whole thing to be, this whole thing to be eventually to be less than C times epsilon over absolute value of C. All right, so that is the proof for number 2. The third limit law has, if you do adding or subtracting the two sequences equals to the sum or the difference of the two limits. So I'm going to do in this video the case where we add the two, and I'll leave it to you as an exercise to do when you do the subtraction. Although it's going to be pretty much the same as what I do in this video. All right, so here's the strategy. We need to find some capital N where the absolute value of our sequence AN plus BN minus our supposed limit A plus B is less than epsilon. All right, this is like our AN minus A kind of thing. So that's what we need to do. We're going to use the knowledge that we have that AN converges to A and BN converges to B. So because AN converges to A, that means there exists some capital N1 so that for all little n bigger than N1, we have the absolute value of AN minus A less than, and I'm calling it epsilon 1. And the similar thing for B, there's a capital N2, where for all little n bigger than capital N2, we have the absolute value of Bn minus B less than epsilon over 2. Or sorry, epsilon 2. And these are arbitrary epsilons. I'm just giving them labels so that we can correspond to each part, I guess, as far as using the convergence of AN to A and then the convergence of BN to B. All right, so that's knowledge that we have. Now, notice if we do the absolute value of AN plus BN minus A plus B, we can rearrange it so it's AN minus A plus BN minus B. And that way we can use the triangle inequality to break that up into the absolute value of AN minus A plus the absolute value of BN minus B. And that's using the triangle inequality, but we need that whole thing to be less than epsilon. So we're going to use our knowledge of AN converges to A and BN converges to B to manipulate it so that we can get the whole thing to be less than epsilon. All right, so certainly if for all epsilon 1, we have that AN minus A, absolute value of that is less than epsilon 1. So since that's for an arbitrary epsilon 1, it'll certainly work for epsilon 1 equal to epsilon divided by 2, where that's our epsilon that we're given, that we're going to say that we're given at the beginning of the proof. And then same thing for the sequence Bn. All right, same thing, we'll get Bn minus B less than epsilon over 2, so that has to hold for all epsilon 2s. So just use the same thing, use epsilon 2 equal to epsilon divided by 2. So that way we have these two being less than epsilon 1 plus epsilon 2. Well, epsilon 1 is epsilon divided by 2, and epsilon 2 is epsilon divided by 2. So that sum is epsilon. So therefore, we're going to have that string of inequalities. So we'd have this. And then that's less than or equal to an minus a plus the absolute value bn minus b, triangle inequality. Well, epsilon or absolute value of an minus a is less than epsilon 1, which epsilon 1 we're using is epsilon divided by 2. So this whole thing is less than epsilon over 2, and same thing for the other one that we're using epsilon over 2, which is equal to epsilon. So therefore we have what our proof should be. Now the question is, how do I choose the corresponding capital N so that I get this result? So what do we use for N? To get this? Because we were using two different values of N for the convergence of those two sequences, AN and BN. And those two values for N are labeled N1 and N2. So which one do we use? Because these two indices might not be the same. So the point in which we have for where Bn converges to B, whatever that cutoff point, doesn't have to be the same cutoff value that you have for An converges to A. All right, so N1 might not be the same as N2. So what we do in order to guarantee the convergence of both sequences, we're going to let N be the maximum of these two, of N1 and N2. And that's going to work. And so it's just to visualize here. So N1 equals N2 is not necessarily true. So we have our two sequences, A1, comma A2, dot, 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 and then AN1, and then AN1 plus 1, and so forth. And then same thing for B's, except we have BN2, and then BN2 plus 1, and then so forth. Now, where these cutoff values happen, they not have to be the same. So what happens when we have capital N1 being greater than the cutoff value capital N2? Now, if that's the case, using the indices corresponding to our sequence A, then we have A1, A2, and then somewhere down the line we have A index N2, and then A index N2 plus 1, dot, 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 and then somewhere we have A index N1, comma, and then A index N1 plus 1, dot, dot, dot. Now we know for A's that we need all of the A's, all of the indices N bigger than capital N1 to guarantee that the sequence converges to A. So these are going to be all the values, all the sequence value terms that lie in our confidence region. And that's absolute value of AN minus A. All right, so that will be less than some epsilon that we're using. All right, but that happens here. Now, the terms that come before that, so these terms that come before that, if we use the indices for those, they might not be in our confidence region. So everything that, all the terms with indices starting at a n 2 and then go bigger than that. So you have a n 2 plus 1, and then like a n 2 plus 2 all the way up to a n 1. So these terms, it's not guaranteed that they're going to be close enough to the limit a. It's not guaranteed they're going to be in our confidence region of a n minus a, the absolute value of that, being less than some arbitrary epsilon. Now this happens, so in other words, we would want to pick the bigger of the two indices in order to guarantee the limit or the sequence converging. So the bigger of the two is n1, so we would pick, in this case, n equal to n1 for an to converge to a. That's if n1 is bigger than n2. But we don't know if it is or not. But whatever the bigger index is, and so the same logic's going to apply for Bn converges to B. So whichever of the two values, n1 and n2, we would pick the larger one so that we're guaranteed that no matter what terms we pick or what terms are beyond that index value, that we're in our confidence regions for both of the sequences as far as an converges to A and Bn converges to B. So I hope that sort of makes sense as far as, this isn't a proof, this is just discussing what value n do we need in order to guarantee that we have this whole thing in order to guarantee this. So what n do we use? And that n is going to be the maximum of n1 and n2, where n1 comes from the convergence of an to, and then n2 comes from the convergence of bn. So in order to be careful here, in order so that we have it to both of them converge, we have to pick the larger index value. Because if we don't pick the larger index value, it's not guaranteed that some of the terms with indices before that are going to lie in our confidence region. Okay, so that was sort of a mouthful. Now the proof's going to be a lot shorter than this. I figured I'd go in the explanation of which n to use, because a lot of the times you see in a textbook, they just say let n be the max of n1, n2, and it's not really explained. And I figured I would carefully explain that. All right, so the actual proof. All right, so again, we're given some epsilon. Given epsilon greater than 0, and then we're assuming an converges to A and Bn converges to B. So we wish to show that An plus Bn converges to A plus B. Well, what does that mean? So that means we need to, for this epsilon greater than 0, so this means that's if and only if for all epsilon greater than 0, there exists some capital N. So for all little n bigger than capital N, we have the absolute value of the difference of An plus Bn minus A plus B to be less than epsilon. That's what we're trying to show. Okay, so we're going to use the fact that An converges to A and Bn converges to B. So since AN converges to A, there exists some capital N1 so that for all little n bigger than capital N1, we have the absolute value of AN minus A less than epsilon over 2, right? Because we want that to be epsilon over 2, and the same thing for the Bn minus B. Right, and so recall that we were using epsilon over 2 for corresponding epsilon 1 and epsilon 2. All right, so now we have that knowledge, so therefore pick n to equal the maximum of n1 and n2. Then we have for n bigger than capital N, we're going to have the following. So we have the absolute value, AN plus BN minus A plus B. That's equal to absolute value of AN minus A plus Bn minus B by triangle inequality. That's less than or equal to absolute value of AN minus A plus Bn minus B. That's triangle inequality. And we know AN minus A, that absolute value of that's less than epsilon over 2. So this would be less than epsilon over 2, and the same thing for Bn minus B. So that'd be epsilon over 2 plus epsilon over 2, which summing those up, we get epsilon. And that's what we needed to show. So for this n, capital N, it just needs to be the maximum of n1 and n2, where we found n1 and n2 based off of the convergence of AN and the convergence of BN. And we found those two indices, n1 and n2, to be such that we have the difference, the distance of AN with A to be less than epsilon over 2, and the same thing for Bn minus B. All right, so that is the proof for that. And I think I'll end it here. And in the video, I'll start out with the, so that was number 3, I believe. Yeah, so that was number 3 out of those limit laws. I'll let you try the difference one. Pretty identical to this. And then I'm going to start out the next video doing the product one from the limit laws.